Systems of equations and inequalities. By 1943, it was obvious to the Nazi regime that defeat was imminent unless it could build a weapon upon unlimited destructive power, one that had never before been seen in the history of the world. In September, Adolf Hitler ordered German scientists to begin building an atomic bomb. Rumors and whispers began to spread from across the ocean. Refugees and diplomats told of the experiment happening in Norway. However, Franklin D. Roosevelt wasn't sold and even doubted British Prime Minister Winston Churchill's warning. Roosevelt wanted undeniable proof. Fortunately, he soon received the proof he wanted when a group of mathematicians cracked the Enigma code, proving beyond a doubt that Hitler was building an atomic bomb. The next day, Roosevelt gave the order that the United States begin work on the same. The Enigma is perhaps the most famous cryptographic device ever known. It stands as an example of the pivotal role cryptography has played in society. Now, technology has moved cryptanalysis to the digital world. Many ciphers are designed using invertible matrices as the method of message transference, as finding the inverse of a matrix is generally part of the process of decoding. In addition to knowing the matrix and its inverse, the receiver must also know the key that, when used with the matrix inverse, will allow the message to be read. In this chapter, we will investigate matrices and other inverses and various ways to use matrices to solve systems of equations. First, however, we will study systems of equations on their own, linear and nonlinear, and then partial fractions. We will not be breaking any secret codes here, but we will lay the foundation for future courses. Systems of linear equations, two variables. A skateboard manufacturer introduces a new line of boards. The manufacturer tracks its costs, which is the amount it spends to produce the boards, and its revenue, which is the amount it earns through sales of its boards. How can the company determine if it is making a profit with its new line? How many skateboards must be produced and sold before a profit is possible? In this section, we will consider linear equations with two variables to answer these and similar questions. Introduction to systems of equations. In order to investigate situations such as that of the skateboard manufacturer, we need to recognize that we are dealing with more than one variable and likely more than one equation. A system of linear equations consists of two or more linear equations made up of two or more variables, such that all equations in the system are considered simultaneously. To find the unique solution to a system of linear equations, we must find a numerical value for each variable in the system that will satisfy all equations in the system at the same time. Some linear systems may not have a solution, and others may have an infinite number of solutions. In order for a linear system to have a unique solution, there must be at least as many equations as there are variables. Even so, this does not guarantee a unique solution. In this section, we will look at systems of linear equations in two variables, which consist of two equations that contain two different variables. For example, consider the following system of linear equations in two variables. 2x plus y equals 15. 3x minus y equals 5. The solution to a system of linear equations in two variables is any ordered pair that satisfies each equation independently. In this example, the ordered pair 4, 7 is the solution to the system of linear equations. We can verify the solution by substituting the values into each equation to see if the ordered pair satisfies both equations. Shortly, we will investigate methods of finding such a solution if it exists. 2 multiplied by 4 plus 7 equals 15 is true. 3 multiplied by 4 minus 7 equals 5, and that's true. In addition to considering the number of equations and variables, we can categorize systems of linear equations by the number of solutions. A consistent system of equations has at least one solution. A consistent system is considered to be an independent system if it has a single solution, such as the example we just explored. The two lines have different slopes and intersect at one point in the plane. A consistent system is considered to be a dependent system if the equation have the same slope and the same y-intercepts. In other words, the lines coincide, so the equations represent the same line. Every point on the line represents a coordinate pair that satisfies the system. Thus, there are an infinite number of solutions. Another type of system of linear equations is an inconsistent system, which is one in which the equations represent two parallel lines. The lines have the same slope and different y-intercepts. There are no points common to both lines, hence there is no solution to the system. Types of linear systems. There are three types of systems of linear equations in two variables and three types of solutions. An independent system has exactly one solution pair, x, y. The point where the two lines intersect is the only solution. An inconsistent system has no solution. Notice that the two lines are parallel and will never intersect. A dependent system has infinitely many solutions. The lines are coincident. They are the same line, so every coordinate pair on the line is a solution to both equations. Figure 2 compares graphical representations of each type of system. Independent system, inconsistent system, dependent system. How to. Given a system of linear equations and an ordered pair, determine whether the ordered pair is a solution. 1. Substitute the ordered pair into each equation in the system. 2. Determine whether true statements result from the substitution in both equations. If so, the ordered pair is a solution. Solving systems of equations by graphing. There are multiple methods of solving systems of linear equations. For a system of linear equations in two variables, we can determine both the type of system and the solution by graphing the system of equations on the same set of axes. Solve the following system of equations by graphing. Identify the type of system. 2x plus y equals negative 8, x minus y equals negative 1. Solve the first equation for y, solve the second equation for y. Graph both equations on the same set of axes as in figure 4. The lines appear to intersect at the point negative 3, negative 2, and we can check to make sure that this is the solution to the system by substituting the ordered pair into both equations. The solution to the system is the ordered pair negative 3, negative 2, so the system is independent. Q&A. Can graphing be used if the system is inconsistent or dependent? Yes, in both cases, we can still graph the system to determine the type of system and solution. If the two lines are parallel, the system has no solution and it is inconsistent. If the two lines are identical, the system has infinite solutions and is a dependent system. Solving systems of equations by substitution. Solving a linear system in two variables by graphing works well when the solution consists of integer values. But if our solution contains decimals or fractions, it is not the most precise method. We will consider two more methods of solving a system of linear equations that are more precise than graphing. One such method is solving a system of equations by the substitution method, in which we solve one of the equations for one variable and then substitute the result into the second equation to solve for the second variable. Recall that we can solve for one variable at a time, which is the reason the substitution method is both valuable and practical. How to. Given a system of two equations and two variables, solve using the substitution method. 1. Solve one of the two equations for one of the variables in terms of the other. 2. Substitute the expression for this variable into the second equation, then solve for the remaining variable. 3. Substitute that solution into either of the original equations to find the value of the first variable. If possible, write the solution as an ordered pair. 4. Check the solution in both equations. Q&A. Can the substitution method be used to solve any linear system in two variables? Yes, but the method works best if one of the equations contains a coefficient of 1 or negative 1, so that we do not have to deal with fractions. Solving systems of equations in two variables by the addition method. A third method of solving systems of linear equations is the addition method. In this method, we add two terms with the same variable but opposite coefficients so that the sum is 0. Of course, not all systems are set up with the two terms of one variable having opposite coefficients, and often we must adjust one or both of the equations by multiplication so that one variable will be eliminated by addition. How to. Given a system of equations, solve using the addition method. 1. Write both equations with x and y variables on the left side of the equal sign and constants on the right. 2, write one equation above the order, lining up corresponding variables. If one of the variables in the top equation has the opposite coefficient of the same variable in the bottom equation, add the equations together, eliminating one variable. If not, use multiplication by a non-zero number so that one of the variables in the top equation has the opposite coefficient of the same variable in the bottom equation. Then add the equations to eliminate the variable. 3, solve the resulting equation for the remaining variable. 4, substitute that value into one of the original equations and solve for the second variable. And 5, check the solution by substituting the values into the other equation. Identifying inconsistent systems of equations containing two variables. Now that we have had several methods for solving systems of equations, we can use the methods to identify inconsistent systems. Recall that an inconsistent system consists of parallel lines that have the same slope but different y-intercepts. They will never intersect. When searching for a solution to an inconsistent system, we will come up with a false statement such as 12 equals 0. Expressing the solution of a system of dependent equations containing two variables. Recall that a dependent system of equations and two variables is a system in which the two equations represent the same line. Dependent systems have an infinite number of solutions because all of the points on one line are also on the other line. After using substitution or addition, the resulting equation will be an identity, such as 0 equals 0. Using systems of equations to investigate profits. Using what we have learned about systems of equations, we can return to the skateboard manufacturing problem at the beginning of the section. The skateboard manufacturer's revenue function is the function used to calculate the amount of money that comes into the business. It can be represented by the equation R equals XP, where X equals quantity and P equals price. The revenue function is shown in orange in figure 10. The cost function is the function used to calculate the cost of doing business. It includes fixed costs, such as rent and salaries, and variable costs, such as utilities. The cost function is shown in the blue in figure 10. The x-axis represents quantity in hundreds of units, and the y-axis represents either cost or revenue in hundreds of dollars. The point at which the two lines intersect is called the break-even point. When we see from the graph that if 700 units are produced, the cost is $3,300 and the revenue is also $3,300. In other words, the company breaks even if they produce and sell 700 units. They neither make money nor lose money. The shaded region to the right of the break-even point represents quantities for which the company makes a profit. The shaded region to the left represents quantities for which the company suffers a loss. The profit function is the revenue function minus the cost function, written as P of X equals R of X minus C of X. Clearly, knowing the quantity for which the cost equals the revenue is of great importance to the businesses. Systems of linear equations, 3 variables. John received an inheritance of $12,000 that he divided into 3 parts and invested in 3 ways: in a money market fund paying 3% annual interest, in municipal bonds paying 4% annual interest, and in mutual funds paying 7% annual interest. John invested $4,000 more in municipal funds than in municipal bonds. He earned $670 in interest the first year. How much did John invest in each type of fund? Understanding the correct approach to setting up problems such as this one makes finding a solution a matter of following a pattern. We will solve this and similar problems involving 3 equations and 3 variables in this section. Doing so uses similar techniques as those used to solve systems of 2 equations and 2 variables. However, finding solutions to systems of 3 equations requires a bit more organization and a touch of visual gymnastics. Solving systems of 3 equations in 3 variables. In order to solve systems of equations in 3 variables, known as 3x3 systems, the primary tool we will be using is called the Gaussian elimination, named after the prolific German mathematician Carl Friedrich Gauss. While there is no definitive order in which operations are to be performed, there are specific guidelines as to what type of moves can be made. we may number the equations to keep track of the steps we apply. The goal is to eliminate one variable at a time to achieve upper triangular form. The ideal for a 3x3 system because it allows for straightforward back substitution to find a solution XYZ, which we call an ordered triple. A system in upper triangular form looks like the following. AX plus BY plus CZ equals D, EY plus FZ equals G, HZ equals K. The third equation can be solved for Z, and then we back substitute to find Y and X. To write the system in upper triangular form, we can perform the following operations. 1. Interchange the order of any two operations. 2. Multiply both sides of an equation by a non-zero constant. And 3. Add a non-zero multiple of one equation to another equation. The solution set to a 3x3 system is an ordered triple, XYZ. Graphically, the ordered triple defines the point that is the intersection of three planes in space. You can visualize such an intersection by imagining any corner in a rectangular room. A corner is defined by three planes, two adjoining walls, and the floor or ceiling. Any point where two walls and the floor meet represents the intersection of three planes. Number of possible solutions. Figure 2 and 3 illustrate possible solution scenarios for 3x3 systems. Systems that have a single solution are those which, after elimination, result in a solution set consisting of an ordered triple, XYZ. Graphically, the ordered triple defines a point that is the intersection of three planes in space. Systems that have an infinite number of solutions are those which, after elimination, result in an expression that is always true, such as 0 equals 0. Graphically, an infinite number of solutions represents a line or coincident plane that serves as the intersection of three planes in space. Systems that have no solution are those that, after elimination, result in statement that is a contradiction, such as 3 equals 0. Graphically, a system with no solution is represented by three planes with no point in common. How to. Given a linear system of three equations, solve for three unknowns. 1. Pick any pair of equations and solve for one variable. 2. Pick another pair of equations and solve for the same variable. 3. You have created a system of two equations and two unknowns and solve the resulting 2x2 system. And 4. Back substitute known variables into any one of the original equations and solve for the missing variable. Identifying inconsistent systems of equations containing three variables. Just as with systems of equations and two variables, we may come across an inconsistent system of operations in three variables, which means that it does not have a solution that satisfies all three equations. The equations could represent three parallel planes, two parallel planes and one intersecting plane, or three planes that intersect the other two, but not at the same location. The process of elimination will result in a false statement, such as 3 equals 7 or some other contradiction. Expressing the solution of a system of dependent equations containing three variables. We know from working with systems of equations and two variables that a dependent system of equations has an infinite number of solutions. The same is true for dependent systems of equations and three variables. An infinite number of solutions can result from several situations. The three planes could be the same, so that a solution to one equation will be the solution to other equations. All three equations could be different, but they intersect on a line, which has infinite solutions. Or two of the equations could be the same and intersect the third on a line. Access these online resources for additional instruction and practice with systems of three variables. Example 1, system of three equations with three unknown using elimination. Example 2, system of three equations with three unknowns using eliminations. openstackscollege.org